Hi and welcome to the channel. So today we are going to discuss a very interesting probability problem known as Bertrand Paradox. So Bertrand was a French mathematician who wrote a book on probability known as Probability Theory. This is one of the problems from that book only. So the problem statement goes on like, consider an equilateral triangle inscribed in a circle. Now we have to find the probability that if we draw any random chord on the circle, the length of the chord be greater than the side of the triangle. So let's call the length of the chord be L and the side of the triangle be S here. So we have to basically find probability L greater than S. So there have been a catalog of arguments made over this question for the solution's sake, but Bertrand initially gave three proposals. So let's look at them one by one. The first one is known as random endpoints. So what we are doing in this solution is that we are taking any two random endpoints of the chord and we can join them to create our chord. So let's find the probability that this chord be greater than the side S. So if you look carefully, if I fix one of my edges, one of my vertices, let's look at this vertex A. So I can argue that I can rotate my triangle for the vertex to go anywhere. So let's bring my A to this point B. So my figure becomes something like this. This is my A and B, both points. Arguably, I have rotated my triangle and it's very basic that we can rotate the triangle. It's intuitive too. So let there be a chord, this, this, and this. Let's discuss these three cases. So for the case 1, we can say that the length of the chord is less than the triangle S. For case 2, when our endpoint is in this arc, the length of the chord is greater than our side S. And for the case 3, it's equivalent to case 1 only. So very clearly we can write here that our probability that L is greater than S is equals to length of the arc, this one, upon total length of the circle. So that comes out to be 1 by 3. Okay, so now let's look at another argument that has been made. So this is known as random radial point. So what Bertrand said again in another solution is that let's look at our center. This is our center of the circle and let's take any random radius of it. Let this be a radius. So I can argue that if I rotate my triangle in such a way that this is perpendicular to my triangle, these let's make the diagram much more clear. So let's this be my radius, so this be perpendicular, so it will bisect the chord. So now if I say that if I take any random radial point on this radius, let it be here, so the length of the chord will be less than my length of the side of the triangle. But if I take my chord to be over here in this region, the length of the chord will be greater than that of the side of the triangle. So one can tell from here that probability of L being greater than S is clearly equals to half. So if you look, the probability has been the probability that has been calculated is different in both the cases. So let's look at another case too. It's known as random midpoint case. In this one, Bertrand proposed an idea that if I know the midpoint of any chord, let it be this one, I can create my chord distinctively, right? So midpoint is distinct to a chord. Only a midpoint, a chord can have a unique midpoint only. So here, if I have a chord if I have a midpoint, I can generate my unique chord. So let's look at the cases. If I take my midpoint to be here, so I can generate a chord like this, which is perpendicular to the radius of the circle, which joining those points, center and the midpoint. Similarly, if I have my point to be here, my unique chord is this one. If I have my point at my center, my unique chord is a diameter. So what Bertrand said is that, let us draw another circle to make it much more clear. Okay, if I have my point in the region outside this inscribed circle, what will happen is that my unique chord will be less than that of my triangle's side length. So clearly, if we use like trigonometry here, basic angular formation, this is 30°. So we get this side length, this one to be r by 2. This one is r. Okay, so the radius of the triangle of the inscribed circle is r by 2. And if I have my center inside this circle, so the chord that has been formed will be greater than that of the side of the triangle. So clearly we can say from here that if I have my point in this region of the circle, my chord comes out to be greater than the side of the triangle. So the probability of length being greater than s is equals to area of the circle, that is r square by 4 pi r square by 4 whole divided by total area, that is pi r square. So this comes out to be 1 by 4. So if you look at all the three arguments that have been made, it's very evidently clear that the probability is different, but the arguments are you cannot prove them wrong. They are very intuitive in their own sense. So what Bertrand concluded after this was that when it comes to infinite probability spaces, we need to be very, very careful about how randomness is concerned. For example, if you look at them, in the first case, our randomness depend on 2 points, like we were picking 2 random points. But in the second case, we were picking 1 random point on the radius of the circle. In the third case, rather, we were picking a random point inside the circle anywhere. So this is like throwing a dart on the circle